Hello everybody, what I'd like to do in this video is just work out the problems that were part of our review this year, part of our review work anyway. And most recently these problems were used as part of our hallway kind of walkabout with the different problems on posters around the building. And based on feedback I got from a few of you, I thought it might be helpful to have our video that would kind of talk you through these questions. It would offer you all of the questions in their original form so that you can pause the video at any time and work one out and then see how you did. Fast forward or watch through the explanation and see if you did it okay. So I'm just going to kind of get started. There's a bunch of questions. I'll try to do them probably in a couple different videos, but you can jump to the end and see how far it goes. In this video, I'm not sure how far it'll get or how long this will take, but we'll just kind of get started and see how it goes from there. So two major equations that you're going to need to do these problems. For the most part, one is percent concentration. So let me get my pen squared away here a little bit. Percent concentration we use quite often. And then the other is molarity. And so knowing which one is which is usually fairly obvious, but remember that for percent concentration we need solute over the solution, the whole solution, times 100. And that the units tend to be either grams or milliliters in the numerator, and then again grams or milliliters in the denominator, with some combinations of those two. And then the other equation that we're using a whole bunch here is the molarity equation. So molarity equals moles of solute per liter. This is always in those units, moles of solute per liter of solution. And so when you go to put the values into this, those units must be your choices. When we are given a molarity, as we often are, we can sometimes treat it as being moles per 1,000 milliliters in the math. But to calculate molarity itself, you need to use moles over liters. All right, and we'll see a variety of those throughout the questions that are here. So the first question here, calculate the percent concentration of a solution with 85 grams of sodium chloride dissolved in 340 grams of water. So first of all, obviously this is a percent concentration question. We got that right out of the gate right here. And so we need to look at the units. They give us grams of the salt and then grams of the water. It's also helpful if we can recognize that the salt here is the solute, what's being dissolved, and then the water is not the solution. This is the solvent. Water is a pretty good solvent for a lot of things. But neither one of these is the solution by itself. Together they make the solutions total. In this case, total mass. So if we're going to calculate percent concentration, then we're going to go with that equation that we started out with up at the top there. Grams of solute, that would be in this case 85 grams of our sodium chloride. And then on the bottom, grams of solution. The whole solution will include the 340 and the 85 put together, right? So pull out your calculator, add those up, do what you got to do. 340 plus 85 is 425 grams of solution altogether, salt water in this case. And in terms of going ahead and calculating out then the percent concentration, don't forget that that equation calls for it to be times 100 at the end, because everything of course is being expressed as a percentage, and that means putting it in times 100 in at the end to make that work out. Okay? So pull out your calculator, take a look at it, see if you come up with the correct answer on this one, and hopefully you'll find at the very end of this that this comes out to be a 20% solution. Pardon me, 20% solution. And the units on that then will be percent mass by mass, because we're dividing a mass by a mass, grams over grams. So the unit on the end of that is important as well. So that's a percent concentration problem. Number two is more of a describe what you would do question. So it's a little more of a short answer, but it does give us the recipe here to make a 3.5% mass by mass solution. Well, what does that mean to us? What does 3.5% mass by mass mean? That means we have 3.5 grams of solute for every 100 grams of solution. And this question offers us a rather straightforward quantity of solution, 100 grams. So that's perfectly what we want here. So we would simply dissolve 3.5 grams of the solute, which in this case is the ammonium sulfate. And we could write that out as a name here, or we can write it out as a formula if you're comfortable with those formulas. Come up with them in a hurry, or you can look them up. NH4, that's our ammonium sulfate, into how much water would it take to make 100 grams of solution? Well, if 3.5 grams of the solution is the solute, then the total gets to 100 by adding 96.5 grams of water. And specifically, when we make solutions, we use distilled water because we don't want a bunch of other stuff to be in the water. That, like tap water, includes a lot of other ions. We want it to just be ammonium sulfate, okay, for a total of 100 grams of solution, which was what the recipe called for at the beginning. Right? So that's kind of just a quick description of how you do that. So you go get your electronic balance, mass out 3.5 grams of ammonium sulfate, and with your balance, add 96.5 grams of water precisely to get to a total of 100. All right, let's look at number 3. A student weighs an empty beaker on a balance, finds its mass to be 6860. So imagine this is a little bit more of a story then. So empty beaker, pardon me, pen's slipping a little bit. Empty beaker sits at 68.60 grams. So that's just the beaker. And to that, somebody comes along, the student comes along, and adds water. So we've got now the beaker, same beaker, now with some water in it. And the total mass of that is 115.12. So just by subtraction of those two, right, we should be able to figure out exactly how much water is there. So you just subtract those two. And after you do, that represents then 46.52 grams of water that's been put into that beaker. That's how much it increased, right? So that's our solvent in this case. Whenever we see water in one of these problems, it's helpful to remember that the water is the solvent that's going to do the dissolving almost every time. And then to that, it says we're going to add 4.08 grams of glucose, just given to us like that. So we're going to add to that 4.08 grams of glucose, which is a type of sugar, of course, to make a total solution with what mass? Well, if we add all that up, our total solution mass is 50.60 grams of solution. That's our total solution in mass. And that's a helpful number to have because we're certainly here going to be asked for the concentration, percent concentration, mass by mass, right there. So we're going to need the mass of the solute over the total mass of the solution. So mass of the solute, given in the problem, 4.08 grams of glucose, divided by the mass of the solution, 50.60 grams of solution total, water and sugar, and then times 100 to get a percentage, and we get a percentage of 8.06% mass by mass. And we could say 8.06% mass by mass glucose. That's the solute. So there's that one, percent concentration. And it looks like we got one more with percent concentration here. Sodium thiosulfate concentration, 16.2%. What mass of sodium thiosulfate is in 80 grams of solution under this prescription? So it's 16.2% mass by mass. And they want to know how much sodium thiosulfate, oops, let me try that again, is in an 80-gram sample of it. This sodium thiosulfate is the solute. That's what's being dissolved. We can assume it's being dissolved into water. It doesn't say that initially here, but we're going to assume that that's the case. So we'll take the 16.2% and set that equal to our equation, which is solute over solution. Well, they want to know. I make a mistake. I'm looking back now. I realize I think I said solute, but wrote solution. This is actually the solute. Okay, sodium thiosulfate is the solute that's in the solution, not the solution. So the water is the solvent, and together they make the solution. But we're going to use then what mass of sodium thiosulfate solute. That's what they're asking us to find. So that's kind of our X on the top. And then on the bottom, the total amount of solution in this question is 80 grams. They want to know how much solute would be in there. Take it times 100. And then we'll just work out the algebra from there, right? So we need to get the X. Solve for X. As is often the case, we need to divide both sides by 100. That's going to give us 0.162. I said 2 and I wrote 9. 0.162 equals X over 80 grams. right? And then to solve for x, we're basically going to be multiplying those two numbers together. So x equals 12.96 grams of solute. And we can write solute, you could write sodium thiosulfate, you could write its formula. Any one of those is true. It wants to know what mass, 12.96 grams. So just about 13 grams. Now, it wants to know how many moles of sodium thiosulfate are in 80 grams. That's the same thing we were just asked, right? 80 grams of solution, 80 grams of solution. So really what they're asking us to do is take those grams that you just calculated and convert them into moles. Now that would be really handy because that way we could get to a molarity of the solution or something else that might be useful. Based on the number of moles, we could do some stoichiometry or all kinds of things. But we're going to bring that 12.96 grams of our solution, our solute, Na2S2O3. That formula is in the beginning of the problem. And we're going to convert that to moles. So 1 mole of that is equal to, go to the periodic table and add up Na2S2O3. And you should get a mass of around 158.11 grams as the molar mass. One mole, about 158.11 grams. And if we divide that out, well, it's not much. A mole is 158 grams. We have about 13 grams, so it's just a fraction of a mole. I get 0.08197 moles when I punch that in my calculator. All right, that's all they asked us for in B, so that's pretty quick. And then they say, okay, well, what if that solution, 80 grams, is diluted to 250 milliliters with water? And now they want to know the molarity. So they've come kind of all the way around from percent to ending this question on a molarity calculation. We haven't done a molarity yet on this page, so it changes our tune just a little bit to think, wait a second now, can we connect percent concentration to molarity? And absolutely, if you go back and check what that equation is, right? Molarity is moles of solute per liter, however many liters of solution. Well, we've got moles, we just figured that out. And we've got a volume given to us here as 250 milliliters. That's going to be our volume, which we'll have to turn into liters then. But that's where we're going to go with this. So for molarity, that's moles over liters. And we've got moles, 0.08197 moles. And the solution's volume, it's not a whole liter now, it's 250 milliliters. So we're going to divide that by 1,000 to get liters, 0.2500 liters. And then punch that in your calculator, and that'll give you your molarity. You should get an answer of around 0.3279 moles per liter. And that, again, that capital, it's usually in italics, but a capitalized M means moles per liter, represents the molarity of the solution. So there's 3 kind of steps, all within one rather simple prompt and a rather simple solution. 80 grams of this 16.2% sodium thiosulfate solution, and we took it in a bunch of different directions all at one time. It was pretty straightforward.
All right, on these solubility curve related questions, I've just kind of pulled up here the solubility curve that we're usually using in class to help us solve these. And remember, when they're talking about a saturated solution, you want to know that that's right on the curve. So it's important to recognize that in this question they're talking about potassium iodide, Ki, and we want to know which curve that is. So it's, it's right here. You can kind of see it on your sheet there. It's way up in the top corner. And the temperature is 15 degrees. So down here at the bottom we get 15 degrees Celsius. And so you kind of want to just sort of zoom up to the top then and go across to where that runs into the line, right about there, and then read over. So we're at about 140 grams. Okay, so for our work here, 140 grams of potassium iodide in 100 grams of water. And remember, we know it's 100 grams of water because over here on the y-axis of the graph, it's always in 100 grams of water. So what's this question asking? What mass of Ki would you need to dissolve in 50 grams of water? Okay, so they're just cutting the batch down, right? They're just cutting it in half. And only 50 grams of water, which is half of it, how much would I need? Well, you could probably get that one just by kind of eyeballing it, right? If I'm cutting the water in half, I'm going to have to cut my Ki in half. I always go to chocolate chip cookies in my examples because I like them very much. If I'm going to make a half a batch of chocolate chip cookies, I can't imagine why you would do that. But if I'm going to make a half a batch of chocolate chip cookies, I'm only going to need half of everything. Except the chocolate chips, you use a little bit extra because you always use extra. But if you cross multiply and divide here, you're going to get 70, right? 70 grams of Ki is half. And we can do the math, cross multiply, divide, that's what you're going to get. All right, so for a saturated solution, you want to know that you're on the curve, you want to make sure you're looking at the right curve and at the right temperature, and then paying attention to what the recipe is calling for here in our question. What type of solution would contain? Now, is this going to be on the line, like a saturated solution, or is it going to be an unsaturated solution or a supersaturated solution? That's kind of what it's getting at here. Which one are we up against? Well, we want to make sure we kind of consider, again, that they're giving us 80 grams of NaNO3 in 65 grams of water at 60 degrees. Now, I know right away I'm going to have to do some math because I can't even look at the solubility curve and get much information out of it, right? When I'm looking at the curve over on the right here, it needs to be based on me thinking about 100 grams of water. So again, like in the last question, we need to adjust our recipe a little bit here and figure out, okay, well, what does that equal to? What does 80 grams in 65 grams of water equal to in the terms that I can actually use then to look at my solubility curve, which is, again, always based on 100 grams of water. So we do a little cross multiplication again with our ratio here and figure out what x would come out to be. And if we do, x should be around 123 grams of NaNO3. Now I can go to my curve and look it up because that's in 100 grams of water. Okay, those two are related to each other. And my curve over on the other side of my screen here again is based always on 100 grams of water. So let's clean that off and try. Now, what's our temperature? 60 degrees. All right, so I want to start at 60. I want to go up and see at 123 grams. What would we be looking at here? A little bit bigger dot for us. 123 would be at 60 degrees. 123. That puts me right about here. Okay. And then what's my curve? NaNO3. So I want to be looking at the NaNO3 curve. And that's, well, turns out that that's the one I'm on, right? So I'm dead on the money on the curve at about 123 grams. So on the curve means we've got a saturated solution. On the curve means the maximum amount has been dissolved. Saturated. If we hadn't done our math in advance and figured out that this was equivalent to 123 grams, we'd have been over here on the solubility curve at 80, and that would have put us, way down here somewhere and well under the curve. You have to adjust for the recipe that you're looking at, for the scenario that you're given, before you can go to that solubility curve and use it. You have to make sure you're talking about 100 grams of water. All right. Now, 7 says if you have a solution with 75 grams of KNO3 dissolved in 200 grams of water at 65 degrees, how much more KNO3 would you need to make a saturated solution at 65 degrees? Well, let's go over to our curve and talk about that. Where is a saturated solution at 65 degrees for KNO3? Well, scale is up just a little bit. 65 degrees, right about here, 65. And KNO3 would be, let's see, up we go to the curve, puts me right about there. Okay. So I'm going to say that's about 125 grams of KNO3 in 100 grams of water. So just kind of make myself a note here of that. 125 grams of KNO3 in 100 grams of water is a saturated solution. I'm just kind of writing that down because that's our target. We're trying to make a saturated solution. We need to make a saturated solution, but we're not using 100 grams of water. How much are we using? 200 grams. So if this is saturated, if this is the recipe for a saturated solution of KNO3 at this temperature, well, how much would we need then for 200 grams of water at that same? I'm going to double the batch, right? I'm just increasing my water times 2. How much KNO3 would I need in order to make a solution of that sort? Well, if we imagine doubling the water, we're going to have to double the salt too, double the KNO3. So X is 250 grams needed in order to make the solution be saturated. How much do I have dissolved so far? Well, it says I have 75 grams dissolved already. So I already have 75 grams so far, or in advance. And how much more will I need to add? I'm going to need another 175 grams that I'll have to add. So I'm going to have to add 175 more. It's kind of like saying I have a goal of saving $250, and so far I've saved 75. How much more will I need to save to get to my goal? In this case, the goal being a saturated solution, we needed 250 grams. We already had 75 in the solution. There's still room for another 175 more grams in order to make that work. Okay. Two more with our solubility curves. What mass of NH3 gas will need to be dissolved in order to make a saturated solution in 1,000 grams of water? Now, if you're looking at this problem in the current year, there isn't a temperature here, and I forgot to add a temperature. My bad. So I'm going to just pick one so we can solve the problem, and I'm going to pick the one that I'm going to put on this question the next time I use it, so that this answer video will still be accurate. I'm going to say we're at 50 degrees Celsius. I'm just picking a number. If you've already looked at this and you're like, Bluff, I can't do this. There's no temperature. You're absolutely right. I've had a couple students ask that already because you guys are sharp. You notice things like that. But I'm just going to pick a temp. And if you've already picked a different temp, you run with it and see if you get a similar answer. It's actually pretty simple because we're going into 1,000 grams of water. That's 10 times the normal batch, right? Because the normal batch is 100 grams of water. So we're just going to need to look at the curve and multiply it times 10 in order to make this work. So at 50 degrees, ammonia's curve is one of these dashed line curves. Comes right down through the screen. At 50 degrees, that would be, let's see, up to here and over to here. That puts me at 30 grams. So for our story, that'd be 30 grams of NH3 in 100 grams of water. And they want us to get to 1,000 grams of water. Well, that's times 10, right? So X would be 300 grams needed. 300 grams of ammonia to prepare a 10 times the normal batch solution of ammonia at this temperature. And again, I just picked 50 degrees because I forgot to do a temperature. Any temperature you could read off the curve and just take your answer times 10 for this question, and you'd have the right answer for your temp as well. Okay, one more question on solubility curves. If you have a solution containing 140 grams of NaNO3, okay, in 250 grams of water. That's what I have now at 15 degrees Celsius. How much more would you need to dissolve in order to make a saturated solution? Hopefully you recognize that this looks a lot like question 7. You have a solution containing at this temp, how much more would you need to add? So I'm going to let you work this one out the same way we worked out number 7. Figure out what a saturated solution of NaNO3 will be at this temperature, and then take it the rest of the way from there. Okay? We'll get you started by just making sure that we're all looking at the right curve and getting the right number. This is what my solution is. I'm going to make a note because I don't want myself getting confused later and thinking that that's saturated. This is just my current solution right now. What is saturated? Let's define it based on the temperature and the solute that's been given. 15 degrees Celsius, so right here. And we're looking at NaNO3. That's way up near the top here. 15 degrees puts me right about there. I'm going to read over to the side. Let's call that 82 grams of NaNO3 in every 100 grams of water. Oh, what the heck. Let's just finish it out. If you don't want to listen, you go ahead and pause it or stop it. Fast forward, see if you get it right later. Okay. If that's saturated solution in 100 grams of water, what will a saturated solution be in 250 grams of water? Again, like before, we're sort of scaling up the size of our recipe from 100 to 250. So cross multiply and divide, and you should get an X that's around 207.5. That's not going to work. I got 82 times 250 divided by 100. 205. That's how much I'm going to need. I currently have 140. There's 205 needed. I have 140 grams. I'm going to need another 65 grams for this to be saturated. Okay.
And we'll pick it up with number 10 now. So number 10 is a titration question. And titration problems tend to be based on molarities because when we're using titrations and looking at an acid and a base, for example, we're usually looking at them in terms of a chemical reaction equation that's been balanced. And in a balanced equation, everything needs to be considered in terms of moles and molarity, not grams or percent concentration. So you'll see a lot of molarities involved with titration-related problems like this one. And it's saying here we need to titrate an acid. So I'm going to do that with red, because usually we think about acids as red, like with red litmus paper. 22.3 milliliters of acid. And then we're using a base, which of course is how you titrate an acid. We're using a base here with a concentration of 0.1202. And the burette readings for the KOH, for the base, are 2.07 and 18.66. That's the final volume reading on the burette. What is the molarity of the acid? So I'm going to show this to you two ways. Actually, yeah, I'm going to show it to you the way we've been doing it, I guess, in class, first of all. And keep in mind when you're doing a titration calculation and they're giving you two burette readings, remember that's the before and the after. So just kind of a quick throwback to that in case you've forgotten it. That a burette's that tall, skinny thing with a little dropper tip at the bottom and a little valve kind of right in here that we can use to control it. And we add drops. But we measure this volume before and after to see how much was dispensed or used from that burette. So they're saying that at the beginning it was at 2.07 and at the end it was at 18.66 milliliters. So the difference between those two then is our number that we'll need to use in order to start the calculation for this, because that's the volume of base that was used. And we need to start our work with the base's volume, because that's what we know the concentration of. You want to start the problem with the thing that you do know about, so that at the end you can solve for the thing that you don't know about, that you're being asked for. So in this case, we have to subtract 18.66 minus 2.07 to figure out how much of the base in this part of the picture here was what was being used. And if you subtract, you'll find that it's 16.59 milliliters of the KOH, of the base. Now, that's milliliters. We need to get that over then into moles, because remember, with a neutralization in a titration reaction like this, we need to consider it as a mole-to-mole ratio, and what that ratio is going to be. So let's first get this to moles. It says in the problem that it's a 0.1202 moles per liter solution. That's 0.1202 moles of KOH for every liter of solution, or since this problem is giving me information in milliliters, let's go ahead and use down here 1,000 milliliters. Some of you will prefer to convert the initial volume at 16.59 into liters and then just use a 1 on the bottom, but either way should work out. You're going to have to convert to liters at some point in order to make this work. And if I stopped right here, I'd have an answer on my calculation of moles of base, but we want to go one step further before we go to the calculator, I think. And that step then is to make sure that we're converting all the way through from moles of base and connecting that over to moles of acid. Okay. So I'm going to take a moment here just to kind of give myself a little working room, because I'm sort of working into my space with the picture here. So you mind if I just kind of white this out a little bit and cheat so I don't have to start all over again. In this next step, we want to think about the base and the acid and say, what is the ratio? Moles of KOH to moles of the acid, and it calls it acetic acid, right? So acetic acid is like vinegar, and we titrated. We should have titrated vinegar in class. I think y'all did. If you're part of my class this year, as I record this, you did. Acetic acid is vinegar. That's HC2H3O2. And you can just Google acetic acid if you need to, and you'll find that formula as well. Now, remember, as far as deciding on the ratio between these, we could look at a chemical equation, or we can just look at it here and say, this acid has one hydrogen. And remember, you look at the front of the formula to find the hydrogen that the acid can use. That's what makes an acid an acid. It has the ability to add hydrogen ions to solution in some way. And the base has one OH group on it. And the reason those are the parts that we look at again, remember, is because H and OH come together to make water. So if I take the H, that's a hydrogen ion, and then I add to that an OH ion, we're going to get a water molecule, right? So that's why we consider just those important parts. That's going to give us our water as we neutralize this. And so we need to look at our acid and base formulas and decide what is the ratio of acid to base. In this case, we've got 1 hydrogen and we've got 1 OH. So those are going to combine perfectly, and that makes this a 1-to-1 ratio. 1 base for every one acid. And now I can go to my calculator and I can punch this in. Because now, if I've canceled out my units, milliliters will cancel, moles of KOH will cancel, and I'll have moles of acid. And that's just going to leave us one short step away from our final answer on this problem. So go to your calculator, punch that in, and check that you should get the same answer I do. I get 0.00199 moles of the acid. Okay, I'm just going to write acid because that's good enough. They want us to figure out the molarity. And remember, molarity is moles per some number of liters as the calculation goes in our problem here. So we're going to take that number of moles, 0.00199 moles of acid, and divide by the volume of the solution, of the acid solution in liters. And again, if I go back up to my problem, it says that the acid solution was 22.3 milliliters. We need that in liters, so I'm going to move my decimal over 3 times. 0.0223 liters. And I've been telling some people this too, and this may help you. Some of you I know just every once in a while will get stumbled up on which way do I move my decimal point to get acid, or a volume rather, converted from milliliters to liters. It's helpful maybe for you to remember that when you're going to liters, like we are here, milliliters to liters, that you move your decimal to the left. So liters, to go to liters, move the decimal point to the left. And then to get to milliliters, you have to go the other way, which is to the right. And that one doesn't really stick as well. But left for liters, and then right for milliliters. So we'd be going left 3. 1, 2, 3. And that gives us that 0.0223, right? So that's where that volume's coming from that we're using now down here. And if I punch that in and divide, I'll get the concentration of my acid. I get 0.0894 moles per liter, or just a big M, of our acid solution. And that's pretty mild acid solution, but works out for this problem. Okay, so that's a titration, number 10, using a story or a situation with a burette that honestly looks probably like a lot like the ones that you've already done and before. Okay, now 11. I see my 11 got kind of close to my 12 here. I'm sorry about that. 11 is a two-step problem that has to do with neutralization too. It's a sort of a titration in a large-scale sort of emergency cleanup fashion. And this question's asking us about cleaning up a hydrochloric acid spill. Hydrochloric acid, it says here, is used to clean brick and masonry. If you need to buy hydrochloric acid to do that in your yard, or in your pavement, or on a building, if you work in sort of maintenance or something like that, you can actually buy hydrochloric acid for that very purpose. They sell it at places like Menards, and it goes by the name muriatic acid. It's a certain concentration. It's pretty potent stuff, so you shouldn't mess around with it. But it is a fact that it's out there. It's used by people for things like that. And we know, hopefully you know, that hydrochloric acid is the sort of predominant acid in your stomach too. So you've got this acid around. It's kind of a common one. So this particular truck is a pretty big truck. It's got 22,500 liters in it. That's a bunch. All right, so we're looking at like a 5,000 or 6,000 gallon truck of hydrochloric acid that's dumping out all over the place. And it's got its molarity at 6.83 moles per liter. It says that they're going to come and neutralize the acid by putting sodium carbonate on it. So sodium carbonate is a base of sorts. It doesn't look like a base in quite the same way, but it reacts according to this equation down below. And if you take a look at that equation, you'll see the hydrochloric acid with the sodium carbonate there. And from that is coming out salt, which makes this sound a little bit like a titration, and water, which makes this sound a lot like a titration, and carbon dioxide gas. Carbonates, it turns out, like sodium carbonate, react with acid and they fizz. So this is a very close cousin to the reaction of baking soda and vinegar. That's what you're looking at here. Sodium bicarbonate. In the case of vinegar, this is sodium carbonate. A little bit more of a base even still. But anyway, we're going to neutralize the acid with the base. And it's asking how many moles of HCl will have to be neutralized. So really that's the first part. How many moles of HCl will there be in this solution that's described right here? Well, moles is going to be volume times molarity, and you'll see in the units again why. But if we think about our original equation, molarity equals moles over liters, and they want us to figure out the moles. Well, we've got molarity, that's right here. We've got liters, that's right here. If you plug those into that equation, you'll have to cross multiply to get moles, and you'll have molarity times volume to get there. You'll also see that it kind of makes sense if we just sort of start out here with the units, 22,500 liters, and I have a 6.83 moles per liter solution. Oops, 6.83 moles of HCl for every 1 liter of solution. So this is going to be some big numbers, right? Because we're taking a rather large amount of acid and taking it times 6.83 moles for every one of those liters. At that point, we can calculate it out, find out how many moles we're talking about. Okay. So if you haven't already done so, okay, take your calculator and punch that in. I'm going to have to get my calculator up and do it myself because I, for some reason, do not have this answer handy, and I for some reason don't have it on my notes here from before. So I'm just going to take my calculator. 22,500 times 6.83 gives me, holy smokes, that's a bunch. We've got 150. Let's just go 154,000 moles, just to kind of round that off. Okay, so it's a big number. It's a pretty big number. All right. That's a bunch of acid. And so you can kind of get a sense a little bit maybe of why these sorts of spills are so substantial, because we're talking about ginormous quantities of chemical that are spilled all over the place. Okay. Now, if that's the amount of acid that needs to be neutralized, how much sodium carbonate will the authorities need to bring out to do this? This is important why, a truck that's traveling with dangerous chemicals like this, we need to know how much is in that truck. Because if the darn thing would spill and leak all over the place, we'd need to know as emergency cleanup personnel or something, exactly how much neutralizing chemical we'd need, or at least what the minimum would be that we'd have to haul out there and really, really fast to dump on there and neutralize the acid. And this is kind of how they do it, because you need to neutralize acid like this as quickly as you can so that it doesn't seep into the ground and affect groundwater or kill off the ground ability to grow plants and that sort of thing. Just soil health, we have to maintain it by neutralizing it. And so they dump this stuff on there, and it gives us pretty mild ingredients. You'll notice here salt, water, and CO2. Those things won't be nearly as hazardous. So it wants to know what mass of sodium carbonate will be needed to neutralize all of the acid. And that's an important little thing at the end that we can kind of throw away, but it's not a throwaway. We need that. What is all of the acid? Well, we just figured out that's 154,000 moles. That's a whole bunch. And we need to neutralize all of it. Well, according to our chemical equation here, we're going to need, for every 2 moles of acid, we're going to need 1 mole of sodium carbonate. So 2 moles of HCl. Let's try that again. 2 moles of HCl. We'll need 1 mole of our sodium carbonate. And then that, if we stopped, would give us moles. We want to take it one step further because they want to know in mass, what mass of sodium carbonate is needed. Authorities will measure things out in mass more often than they would measure things out in moles by the bag. So we need to go one more step. 1 mole of sodium carbonate would be how many grams? So go to the periodic table and add up Na2CO3. I think you can do that. You'll get about 106.1 grams for every mole. And so to finish this problem out, we just punch that into our calculator and figure out what is the necessary amount of chemical to make this neutralization happen. So 154,000 divided by 2, and then times 106.1 gives us our answer. And we're looking at a total of that's 8,170,000 grams of sodium carbonate. Like, wait a second, how much is that? Well, in kilograms, that would be 8,170 kilograms. So it's a pretty large amount, but you could put that on a semi and haul it out there.
All right, let's continue with question number 12 on our solutions review. This one wants us to figure out a volume of stock solution. And stock solution basically just means the original solution. So you have a solution that you'd keep in the stock room, and we call that a stock solution. It's just sort of the one that we keep in the back, and then from that we dilute it down to other concentrations whatever we need based on the lab or based on the experiment that we want to do. So in this case, the 3 molar solution is the stock solution. Usually we're taking a more concentrated solution and diluting it down to something less. In this case, that something less is here at 0.125 molar. Now I'm going to show you 2 ways that we can calculate number 12, and then from here on out, whenever you're doing a dilution question, you can use the shortcut equation if you'd like. They're both based around exactly the same math. But the second one, the shortcut, is obviously a lot quicker, and I would certainly suggest that you use it if you're comfortable using it, and I think you probably will be. So in this case, we need to figure out how many moles of HCl we need in our final solution. So I'm going to take that 500 milliliters and this 0.125 molarity that we've got, and first of all use those to figure out how many moles of solution that we'll need in the solution that we're trying to make, or rather moles of solute that we'll need in the solution that we're trying to make. So 500 milliliters is half a liter. This is 0.125 moles of HCl for every liter. And so if we multiply that out, right, get that in your calculator, we should come up with, for number 12, 0.0625 moles of HCl. That's what we need to have in our final solution. Well, we can take those moles then and see in a 3 molar solution, which is our original stock solution, concentrated one, if we need 0.0625 moles, what volume of that will we need? And that's what it's asking us, right? What volume of the original solution will you need? And if you go ahead and here solve for x, do your math and solve for x, you'll get 0.0208 liters, which is the same as 20.8 milliliters. Okay? So whichever one of those you're comfortable with is fine. Now, I want to show you that shorter method to get the same answer. And it uses an equation that's pretty popular. It's kind of a little handy-dandy pocket-sized equation that you can use in a blink for dilution questions specifically. And that equation is this. It's M1 V1 equals M2 V2. And here the 1s and 2s mean, like in the first solution and the second solution, you could also think about it as the before and after, or in the case of many of these, that one of them is the stock solution. So this is what I keep in the storeroom, original solution, and this is our new solution that we're making from it, usually diluting it down. So however you want to think about it, and it doesn't matter which one is number 1 and which one is number 2, but these M's and V's are for our 2 solutions, and they stand for molarity and volume. So M is for molarity, and V is for volume. The nice thing about this is that volume, when we use this equation, volume can be in milliliters or liters, as long as both volumes are in the same units. And then molarity is just whatever the problem is giving you in molarity, moles per liter. So let's just kind of plug in and set this one up that same way that we just solved it here in red. I'm going to do it now in blue with this equation instead, and see if we don't get exactly the same answer. Okay? So our stock solution, the original solution, is 3 moles per liter. I don't know how much of that I need, so V1, pardon me, got a little loose and goose there. Our V1 is our unknown. That's like my X, right? On the other side of the equation, my M2, my new molarity, is going to be 0.125 according to this problem. And how much of that do I need? 500 milliliters. I'm just going to go ahead and leave it in 500 milliliters because I don't have to change it into liters to use this equation. It's kind of handy, right? If I go to my calculator, I'm just going to double check, punch this one in. 0.125 times 500 divided, we're going to do both sides divided by 3. Okay, so 0.125 times 500 divided by 3, and we get 20.8. V1 equals 20.8 milliliters. And notice there that, again, this all cancels out, and my molarities cancel out, so that leaves my units in milliliters. And sure enough, 20.8 milliliters is exactly what we got before. So that's a little bit quicker way of organizing the same thing, and you can kind of do it all in one step. In the end, notice what we did. We took 0.125, right, times 500, divided by 3. And if you look at what we did up above in the math in the red, we took 500 milliliters, 0.5 liters, times 0.125. And then down here, when we did our algebra, we divided by 3. So it's exactly the same algebra, it's just organized a little bit differently. And I think that equation's really handy then for that. So if you can keep this one around, M1 V1 equals M2 V2, it works very nicely for dilution questions. Okay. Let's try it on another one. Number 13 says, what is the molarity of a solution prepared by diluting? There's that magic word. And we're not mixing it with anything. We're not trying to change our units much at all. We're just trying to take a concentrated solution and dilute it down. Okay? So now we just need our units to match up, and we can make it work from there. So I'm going to use my equation again. Just going to write it down here one more time. M1V1 equals M2V2. And I won't write it every time, but hopefully you can use it enough to where it pops into your head and it kind of rolls off the tongue too. My original molarity, I'm just going to start here, is 3.79. It's here. I'm going to use 50 milliliters of that solution. So this kind of goes together. That means I've got 50 milliliters of that. And we're going to dilute that down all the way to 2 liters here. Now, it's important that my units do match up. So that's going to be 2,000 milliliters. What they want us to know is what is the molarity, right? So what is the molarity of the solution? So that's going to be my unknown. That's M2. So we're trying to, that's our X. And then my overall volume, 2,000 milliliters. And if I just finish this out, I'll be dividing both sides by 2,000. You wouldn't need to show that math for me, but that's what you'd need to do to solve and get things to cancel out, right? And M2 then should come out to be 0.09475. And you might round it off a little bit tighter. That's fine too. But that's our finished molarity. Now, stop and think about it logically. We started out with a concentration here of 3.79 moles per liter. And we took it all the way from 50 milliliters to 2,000. That's a dramatic decrease in concentration. Think about how much that would be watering it down. And so the concentration went from 3.79 all the way down to 0.094. That's a big drop off in terms of concentration. And it makes sense because we're diluting it down with a lot of water. Okay. Now, this question's got the same sort of information, but it looks a lot wordier, and it tells it to us in more of a story again. But just one more time, I'm going to write that equation down. M1V1 equals M2V2. And let's take a look at the story. A student takes a sample of KOH solution and dilutes it with 100 milliliters of water. The student determines that the diluted solution is 0.046 moles per liter. Okay, but has forgotten to record the volume of the original sample. The concentration of the original is 2.09 molar. So look, we've got 2 concentrations in this problem. I've got 0.046 molar. I'm going to put that in over here as my first molarity. And then we'll see, do I have a volume for that? And then on the other side, the other molarity, 2.09 molarity. And we have a volume that we'll need there. Now, we can't have 2 empty spaces here. One of those has to be known. So up in the problem, the way it's kind of presented to us, which one is it? Okay. The student takes the sample and dilutes it with 100 milliliters of water. Okay. We're going to assume that that's our final volume because we don't have enough information to go anywhere else with it. But that's our diluted solution, right? That's after it's been diluted down. It should be at the lower concentration. So diluted it to 100 milliliters. That's our final volume. That's our weaker volume. And so we're going to go with 100 milliliters right here to solve this. Okay. And then this is our volume to find. Whoa, this is our volume to solve for V2. So divide both sides by 2.09, divide by 2.09. Let's punch that in our calculator too. 0.046 times 100 divided by 2.09, and we get a final answer of 2.2. Now, V2 is 2.2. 2.2 what? And again, this is a molarity. That cancels out. That cancels molarity. And so our volume is in milliliters. So the student took a 2.2 milliliter sample, really small, diluted it all the way to 100 milliliters, and now we've got enough information to kind of complete the puzzle on this and kind of be able to finish the story, know how much was present at the start. So M1V1 equals M2V2, a popular equation for dilutions. And you're going to see those around quite a bit. Let's look at 15. We've got a Monster energy drink story here. That's kind of fun. Some of you might enjoy those. I'm not a big fan of energy drinks. I'm always afraid that if I drink something like that, my heart's just going to explode. So I don't touch them. But I drink coffee. We can get a little caffeine there. Some of these with the sugar and the caffeine. Once you get to be an old guy, it's not ideal. So we're going to start with 54 grams of sugar. That's our solute. Hopefully we'd know, of course, sugar is dissolving into the solution as the solute. So 54 grams of sugar, C6H12O6. Hopefully you remember that one from biology. And they want molarity, so we need moles, right? We need moles over liters. So I'm going to convert this to moles. 1 mole of it, 1 mole of sugar. Go to the periodic table and add all those up. 180.16 grams of C6H12O6. And if I divide that out, right, I'm going to get about 0.30 moles of our sugar. Now that's a lot of sugar already. But what's the volume of our solution? Because remember, molarity, sorry, I'm slipping a little here. Molarity is moles per some number of liters. And so moles, in this case, we've just found it, 0.30 moles. And our final volume is up here as 480 milliliters. Well, we need that in liters. Remember, to get the liters, we move the decimal 3 places to the left for liters. So 0.480 liters in that solution. And then we go divide that out, and we get a molarity of 0.624 moles per liter. That's our concentration then for our Monster Energy drink. That is a lot of sugar. Okay.